Okay, we were talking chapter 12, and last time we got into a couple things. We got into Q, which is the reaction quotient. Remember, Q is pretty much calculated the same way as you do K. So you're going to take your products and you're going to divide them by your reactants. Just like you do with K, you still use the coefficients as the exponents. Everything's pretty much the same. As we talked about, basically, there's kind of a couple of reasons that we do calculate Q. The first real reason is if we want to know if we are at equilibrium or not, it will allow us to determine that. The second thing is if it is not at equilibrium, it will allow us to determine which way it needs to sort of proceed to reach equilibrium. So if you compare Q and it's less than the K value, it is not at equilibrium. And to reach equilibrium, it needs to go towards the product side. If you calculate Q and it does equal K, the system is at equilibrium. And if you calculate Q and it's greater than K, once again, it is not at equilibrium. And to reach equilibrium, we'll have to go towards the reactant side to reach equilibrium. So there is, like we talked about, sort of a straight up Q-type question is commonly asked, and that's really the two things there's usually asked in that type of question is, again, are you at equilibrium? Which way you need to go to reach equilibrium if you're not there? The second place it comes into play is what we were talking about at the end, which is when we are calculating equilibrium concentrations. Reminder, we use what's referred to as ice tables to do that. And again, we got initial, change, and equilibrium. And the change is really what we're looking to solve. And we do represent the change with the letter X typically. And we basically take our equation and the I is the initial concentration. So if you're given just the initial concentrations here of A and B, only the reactants, and not mention anything about the products. Once again, as we talked about last time, it is pretty safe to assume that it's going to be zero. We also could safely assume in this situation that the reaction will proceed in the forward direction, as we only have reactants to begin with at this point. So it's definitely going to go in that direction. We do not need to worry about Q in this situation, again, because there's really no way to calculate Q because we have no information about our products. So we can't actually do the Q calculation in this particular case. Remember that when we do this, the X is the change part. And since we can feel confident that this reaction is heading in the forward direction, that means our reactants should be decreasing with time. And we represent that with minuses, and that'll be minus X, minus X. Now, this is not just, again, minus X. It's really minus 1X because we do have to take the coefficients into account for the balanced equation. Much like most things in chemistry, you don't write the 1, but basically it's basically 1x there. On the product side, we're increasing with time since it's heading in the forward direction, so we should have a plus 2x. Once again, those sort of coefficients are really important on the change part because it really does the stoichiometry for you. So it does that correct mole-to-mole relationship in the equation. And again, if you are not using the coefficients, you're going to be off on your stoichiometry and your mole-to-mole relationship, and ultimately you'll be off on your answer as well. When we get down to E, which is the equilibrium line, we're essentially just carrying things down. I also would not maybe put the M's in there so it doesn't look so crowded and extra things. Now, really the goal at this point is to solve for X. We would then use our equilibrium expression in this particular case. And obviously in this problem, we would be given, like the K value would most likely be given to us. At this point, you really have just a math here to solve for. Once again, we would take everything on the equilibrium line basically and stick it into that expression. Now, there are a few different ways that you could solve these problems. But again, as we talked about at the very end last time, a very common way is to use the quadratic formula. And again, that is something like ax squared plus bx plus c equals 0, where x is equal to minus b plus or minus the square root, b squared minus 4ac divided by 2a. So that is, again, one way that you could solve these sort of problems. As we talked about last time, it will give you two x values once you do solve for it. One of those x values will not make sense. And whenever you do solve for x, the purpose of solving for x is so that you could come back to your equilibrium line. And once you determine what the correct x value is, you basically will just put it in on the equilibrium line in all those places. And what that will give you is the equilibrium concentrations in this case for each of those reactants and products. Now, we did this here. We talked about it here in terms of doing it in concentration. We would only, in a case like this, worry about Q if we did have a starting amount of our products. So if we did have a starting amount of our products and our reactants given to us, we would have enough information to calculate Q, and you would want to do that. And as we talked about, I think at the end last time as well, what that would possibly change is the minuses and the pluses, which direction the reaction is going to reach equilibrium. As I said before, probably 99% of the time, it's almost like a no-brainer. It's probably going to be heading toward the right-hand side in the products, and you could almost safely go minus and pluses. But there are a few times that it does pop up that perhaps it might be going in the other direction. And really, again, if you have starting amounts of everybody, you should calculate the Q and worry about it at that point. The other thing is, although we did it here, like I was just about to say, with concentrations, you could do this with a Kp value and do this ice table with pressures as well. And I think earlier we talked about in this chapter that the unit you definitely want to be using is atmospheres. Yeah. So if you have some partial pressures given to you in a problem and they're in some other unit other than atmospheres, they do need to be converted to atmospheres to go into the ice table. And even if they want the answers in some other unit of pressure, you need to kind of atmosphere it in the table and then unatmosphere it after you do the calculation to get the proper answer. Any questions on any of that there? All right, so let's take a look at one here together, kind of work through it and see. I remember how to do it. I don't know. We'll see. 50-50 shot. All right. So let's take a look at this one here. We have an equilibrium constant, Kc, of 7 for this reaction. We got Br2 goes to 2Br. If the initial concentration of Br2 is 0.663 molar, we want to know what is the equilibrium concentrations of everybody here. Pretty much, if you're ever asked a question like equilibrium concentrations, equilibrium pressures, it's probably going to involve an ice table somewhere in that calculation. So you just want to kind of think about that. So let's just start with the expression here. So like normal, our K would be our products, which in this case is Br. We do need to square it because of the coefficient, divided by the concentration of Br2, and that's going to equal lucky number 7 there. Now, we're going to do an ice table here so we could calculate the actual equilibrium concentrations. So we'll start with our equation. And initially, we are only given information about Br2, which is 0.663. Once again, in this case, since we are not given any information about our products, it is definitely safe to assume that we're starting with 0 here on our product side. Because we also, much like our example a second ago, do not have any products, it is also pretty safe to assume this reaction is heading in which direction? It's going to go in the forward direction because basically, again, all we have are reactants. So we got our sort of minuses and pluses worked out in that situation. We should see our reactants decreasing with time. We should see our products increasing with time. And now we could get to the change part. That would mean that this would be minus x. And on the other side, this would be plus 2x. Remember, again, we are using the coefficients here. with the x's, as that will obviously give us, again, the proper stoichiometry there. Now we could get to equilibrium here. And again, all we're going to do is just carry everybody down. So 0.663 minus x, and basically that's just 2x. First off, any questions on the table there? All right, so again, the goal always usually is to solve for x. So we're going to use our expression to do that. So we're going to take everybody on the equilibrium line. We're basically going to put it into our expression that we have for the reaction. And if we do that, that is going to give us 2x on top. We want to make sure that we are going to square it, again, because of the expression. We're going to divide it by 0.663 minus x, and that is going to equal 7 in this case. So we're going to solve this basically and get an equation. The first thing we probably want to do is just take everything on the bottom there and multiply it to the other side. And if I do that, I think I'll come over here. I'm also going to square the top, which will give me 4x squared is equal to try that again here, 0.663 times 7. Going to get me 4.641 minus 7x. So we are going to kind of set this up for a quadratic. Basically means you need to get everybody to the same side of the equal sign. It really doesn't matter which way you go. Most people tend to like to keep the x squared positive, but it really doesn't matter. So I'm going to do that. I'm just going to bring basically everybody on this side to the other side. Remember, when you go to the other side of an equal sign, you do the opposite function. So that will give me 4x squared plus 7x minus 4.641 equals 0. Any questions so far? That is basically my quadratic equation there. That is my A, B, and C. So there's my A, my B, and my C. By the way, the C keeps the negative when you go into the quadratic, yeah. So going into our quadratic formula here of x is equal to minus b plus or minus square root of b squared minus 4ac divided by 2a. That will get me here minus b, which looks like minus 7 plus or minus. If we do inside the square root, taking b squared minus 4 times a, which is 4, times c, which is negative 4.641. That's going to give us, inside the square root, before you square root it, about 123.256, which if you square root it, will get you about, we'll call it 11.102, about 11.102. That's going to be all divided by 2 times a, which is 4 times 2, which is 8. So again, we're going to get our 2x values. We're going to do we'll do the plus first, and then we'll do the minus. So doing the plus version, that's going to give us negative 7 plus 11.102. So I should hit the right number, would be helpful. Divided by 8, going to get us 0.513 as a possible x value. Now going through and doing the minus here, or subtraction, negative 7 subtracting 11.102 divided by 8, going to get us a negative 2.26. First off, any questions so far? So remember that these are our two possible x values, and really we want to pick whichever one, when we put them back into our equilibrium line, will not give us a negative number. So clearly, since this right here is 2x, That one with a negative sign is probably not so good, right? Because that's going to give us a negative concentration. That would obviously give us a negative 4 point something, which means no good. It's going to get us a negative number, right? When we put that back in, that would mean by default, that looks like a winning number there. And now that we have the correct X value here, we can now put it in for each of those guys' equilibrium line. So the concentration of Br2 at equilibrium 0.663 minus X, which is 0.513. This is again molarity. Don't forget to bring the units back here. And that's going to get us, looks like 0.15 molar. For the concentration of Br, that's equal to 2 times X, which would be 2 times 0.513. And that's going to get us, we'll call it 1.0, we'll round it 3 molar in this case. First off, any questions on that there? So this is, again, a little quadratic and stuff. One way you could solve these type of problems. This was a pretty easy sort of quadratic, but they can get a little bit more complicated, obviously, with a lot more factoring. Any questions on any of that? Now, the good thing about math is, usually when you do math, you could kind of check to make sure you didn't screw up too badly, right? How could I check to see if I didn't screw up? What can I do now that I have the equilibrium concentrations? Yeah, exactly. So now that I have the equilibrium concentrations, I can put those concentrations back into this expression. I should get about 7, right? Maybe not exact with rounding, but you should get pretty darn close. So if you pop our numbers back in there, 1 point, we'll take the 3, 1.03 squared, divided by 0.15. I got like 707. That sounds good. Now, it's a good idea to check yourself because, again, there could be places where you screw up along the way in the math part. And if you put your numbers back in, and for this one, you get like 192 for K, you probably screwed up somewhere there. Yeah. So that's a good thing to do. So I'd highly recommend, if you do have time, which you should, hopefully, I would put your numbers back in and make sure you check it just to make sure, you hopefully didn't make too bad of an error somewhere along the way. Again, if it's not perfect, it's okay, but it should definitely be pretty close in the ballpark of what the K value is. If you're significantly off, you probably made some type of math error. Any questions on that there? Okay. Then now that I did one, seems like it's your turn. Why don't you do one here? We got a mixture of 0.5 moles of H2 and 0.5 moles of I2. They're in a 1 liter flask. We're looking for the equilibrium concentrations of each of these guys, H2, I2, HI. The K value is 54.3. And there is our equation. H2 plus I2 goes to 2HI. So take some moments, work through it, see what you come up with. Yeah. What's that? Yeah, so in normal situations, if you come across a problem, it really doesn't mention anything about like the products, it's safe to assume 0. Yeah. Because definitely if there's something there, they would put something in the problem for you. Okay, let's take a look, see how you're doing. So obviously here we're looking for some equilibrium concentrations. So that should again be an ice table situation. We're going to start with our expression. So in this case, we got Q, or not Q, K is equal to the concentration of HI, and we're going to square it, divided by the concentration of H2 and the concentration of I2, and that's going to equal 54.3. So obviously here, to do our ice table, we do need molarity, or the concentration. Here we have moles and liters, which will allow us to calculate the concentration, as it is moles per liter is molarity. So this one's not too bad, 0.5 moles per 1 liter. Going to get us 0.5 molar for our H2. Same thing here for our I2. Going to go 0.5 moles divided by 1 liter, 0.5 molar. Any questions so far? All right, we're ready to do our ice table. I'm going to flip the page here. Maybe I got it. I do got it. Not bad. All right, so we'll rewrite our expression, which is HI squared, H2I2, and that's going to equal 54.3 in this case. All right, so starting with our initial concentration here, 0.5 molar. We got 0.5 molar there. Once again, as was the earlier question, nothing mentioned about HI here. So again, safe to assume that we got 0 or nothing really happening there on the initial. Also, because of that, it is safe to assume that this reaction should be heading again in the forward direction, which means our reactant should be decreasing with time and our product should be increasing with time. So we're going to go minus x, again, making sure we use our coefficients. Minus x, remember on the right-hand side, it is plus 2x. Again, sometimes people go minus minus and keep minusing on the other side. So remember, it is plus on that side. To our equilibrium, we're just going to drop everything down here, 0.5 minus x, 0.5 minus x, and 2x. Any questions on the ice table or anything like that? Okay. All right, so just like previously, we're going to take our entire equilibrium line basically and put it into our expression so that we can solve for what x equals. And if we do that there, that's going to get us a 2x squared divided by 0.5 minus x, 0.5 minus x, and that will equal 54.3. So obviously here we do want to solve for x. Hopefully you recognize this is a perfect square. Yeah. So you don't always have the quadratic, yes, but sometimes you do. In this case, you don't need to actually do the quadratic. You take a little perfect square action on both sides, maybe a little easier. So that's going to give us 2x on top, 0.5 minus x on the bottom. And the thing I personally forget to do most of the time is actually take the square root there of 54.3 on the other side. And that's going to get me a, looks like 7.3689. All right, so that looks a little easier perhaps to solve. We're going to multiply what's on the bottom to the other side. So we're going to take this guy to the other side, and that will get us 2x is equal to 0.5 times 7.3689. Looks like 3.68445 minus 7.3689x. Going to bring our x's to the same size, so I'm going to bring this guy back that way. Going to get me 9.3689x equals 3.68445. Lastly, we're going to do a little dividing action there. And we will end up with, I hope, a number. Looks like x is going to equal 0.393 in this case. Any questions on that there? Nothing really to check here. That is the x value. By the way, if you quadratic it out, you should get the same number, believe it or not, just a little longer of a process in this particular one. So that, again, is the x value we have in our equilibrium line, and that's what's going to allow us to get to our equilibrium concentrations for everybody. So we're just going to plug that in, and looks like for our H2 concentration, that would be 0.5 minus x, which would be 0.393 molar. Don't forget, again, when you're giving concentration units, to include the units in your answers and put it back in at the end. 0.107 molar. We should end up pretty much identical there for I2, since it's the same calculation, 0.5 minus 0.393 molar, 0.107 molar for that one. And lastly here for our HI at equilibrium, that is 2 times X, or 2 times 0.393 molar. And that's going to get us 2 times 0.393, 0.786 looks like. And those should be our equilibrium concentrations here. Once again, we could check it. So if I take my 0.786 and do a little squaring of it and divide it by 0.107 and divide it by 0.107 one more time, I end up with 53.96 or 54, which is pretty close to my equilibrium constant value. So once again, once you have your equilibrium concentrations, you can stick it back in there and make sure it's pretty close to the K value. Any questions on any of those steps? So again, this is another way that we could solve these problems. You get a perfect square. I would take it. Maybe it's easier to do. Not all situations can you do a perfect square. You do have to have that on both sides. If not, you can quadratic it. Any questions? Okay. All right, let's test your math out here on this one. The initial concentrations of H2, I2, and HI in this reaction, same reaction, same K value, 54.3. We got for H2 0.00623 molar, 0.00414 molar for I2, and 0.0224 molar for your HI. So we're looking for everybody's equilibrium concentrations. I will rest as you calculate. I'm going to sit down for this one, I think. All right. All right. So we have the initial concentrations given to us. And obviously, we could have our K expression, which is going to be the same K expression we had last time. Concentration HI squared divided by H2 and I2, and that's going to equal our 54.3. In this case, we do see the concentrations of everybody given to us. This again would be a good idea perhaps to calculate Q as well. So you have the opportunity to do that because you're given everything, although it does tell us its initial concentrations, and we are looking for equilibrium concentrations. What this really will help us decide is when we get to our ice table, are we doing our minuses and pluses sort of in the right direction? I would imagine that it's not going to tell us we're at equilibrium. Otherwise, it wouldn't be much of a problem to do. So let's do that. So Q, again, is calculated the same way. So we're going to take concentration of HI, square it, divided by H2 and our I2. And we're going to put our initial concentrations in here. So we got 0.0224. Again, we're going to square it. Divided by 0.00623 times it by 0.00414, and that will give us our Q value here, and that's going to be 0.0224 squared divided by 0.00623. It equals divided by 0.00414. Going to get us about a 19.5 for our Q value. So obviously in this case, Q does not equal K, and Q in this case actually is less than K. So again, the first thing it tells us is it's not at equilibrium, which is probably not a big surprise because we're asked for the equilibrium concentrations. But more importantly, in order to reach equilibrium, which way does it need to go? Needs to go opposite the way that guy's pointing. It needs to go to the product side, right? Which means it needs the forward direction of this reaction to take place. So now we can feel confident when we do our ice table that our minuses and pluses, again, are on the sort of correct side. Any questions why we would want to calculate Q in this situation? Obviously, in the previous problem, there was no way to calculate Q because we were not given any product information. So again, you don't have to worry about it in that situation. All right, now that we are confident, hopefully, about which way this thing is going, Let's do the actual ice table. So I'm gonna borrow maybe a page here. So we got H2 plus I2 goes to 2HI. We'll pop our K in here again. Gonna be our HI squared. H2I2 54.3. All right, so rolling with our initial concentrations here. So for H2, 0.00623, 0.00414 for the I2, and not zero in this case. Actually, have an initial concentration, right, for our HI of 0.0224. We calculated Q, so we know confidently that this reaction is heading in the forward direction to reach equilibrium. So we're going to do our same change, minus x, minus x. A reminder that on the right-hand side, this is plus 2x. Sometimes at this point, people are so used to doing the minuses after a number that they automatically go like minus 2x on the right-hand side. Yeah, so just keep that in mind. We're going to drop that down. 0.00623 minus x, 0.00414 minus x, and 0.0224 plus 2x. Any questions on the table there? All right, so we're going to go into our equilibrium here expression. That's going to get us here 0.0224 plus 2x. We're going to square it and be sad about that. And we're going to take 0.00623 and minus x and 0.00414 on the bottom there, minus x equals 54.3. Well, not a perfect square, right? So math time, right? So we got to factor out the top, factor out the bottom, FOIL method, in and out, whatever you learned, right? So you got to go in and out to each of those. So I'm going to personally just kind of do them separately. I'm going to do the top first and then do the bottom, put it all back together and see. And then screw up too badly. We'll see. All right. So why don't we just start with the top here? Maybe I'll just do this, put a little box that away. All right. So on the top, we got here 0.0224 plus 2x, 0.0224 plus 2x, and again, hopefully, right, in and out, right, and in and out on both sides, right? So if you do that, I'm going to go a little scientific notation just so I don't have so many zeros flopping around in my numbers. That gets you 5.018 times 10 to the minus 4 plus 4.48 times 10 to the minus 2x plus 4.48 times 10 to the minus 2x plus 4x squared. I'm going to combine my x's, and that's going to give me for the top part of the left-hand side 4x squared plus 8.96 times 10 to the minus 2x plus looks like 5.018 times 10 to the minus 4. All right, so that is basically right here, what we just did. So now I'm going to do the same thing for the bottom. Maybe we'll do it in orange. Maybe we'll do it in black. All right, so I'm going to do here. And we'll do the bottom, same deal. So we got 0.00623 minus x, 0.00414 minus x. Again, same thing, sort of in and out. And that's going to get us here. Still my calculator here. 0.00623 times 0.00414. Going to get us a 2.579 times 10 to the minus 5. We're going to go minus 0.00623x minus 0.00414x, again by going in and out on both sides. And that's going to get us a plus x squared. Once again here, combining my two x's, going to get us for the bottom x squared. We got there x squared. There it is. Minus 1.037 times 10 to the minus 2x plus 2.579 times 10 to the minus 5. Any questions? Again, with rounding, you might have a slightly different number if you round a little bit more than I did. I didn't round too much along the way. And obviously, I put in scientific notation, so I had to have a bunch of zeros kind of all over the place. All right, so now that we have the top and now that we have the bottom, we are going to put it back together. So I'm going to flip the page here to get a little bit more room, I think, and recopy that. So up on top, we have 4x squared plus 8.96 times 10 to the minus 2x plus 5.018 times 10 to the minus 4. On the bottom, we settled there with x squared minus 1.037 times 10 to the minus 2x and 2.579 times 10 to the minus 5. That still equals 54.3. All right, next big deal here is we're going to take the bottom right, and we're now going to multiply it all the way to the other side carefully. Nothing's going to change on top, so that will still be 4x squared plus 8.96 times 10 to the minus 2x plus 5.018 times 10 to the minus 4. When I multiply that bottom to the other side, we will end up with 54.3x squared minus 5.63 times 10 to the minus 1x plus 1.40 times 10 to the minus 3. And again, just multiplying everybody on the bottom by 54.3. All right, almost there. Going to combine. Again, I'm going to take everybody on the left-hand side here. I'm going to move it to the other side just to keep my x squared positive. It doesn't really matter, but that's just the way I'm going to do it. And when I do that, finally, basically 54.3 minus 4 gives us a 50.3x squared. We'll take our x value on the left-hand side and subtract it from our x value on the right-hand side, and that is going to yield us a minus 6.53 times 10 to the minus 1. That should be x, I believe. And last, we're going to take our 1.4 times 10 to the minus 3 and subtract this number right there from it. And that's going to yield us an 8.98 times 10 to the minus 4 is equal to 0. Any questions on that so far? All right, that should be, dare I say, our A, B, and C action for our quadratic, right? All right, so putting that into our quadratic, x is equal to our minus b, which would then turn that into a positive 6.53 times 10 to the minus 1, plus or minus our square root of b squared minus 4 times a times c. If you do all that inside the square root before you take the square root, 2.457 times 10 to the minus 1. After you square root it, a little 4.957 times 10 to the minus 1. All that's going to be divided by 2 times 50.3, which is going to yield you 100.6 on the bottom. We're going to do our two x values. We'll take our plus and our minus. And I believe if you do the plus there, one x answer you will get will be something like 1.14 times 10 to the minus 2. The other x answer will be 1.56 times 10 to the minus 3 by doing the subtraction of the top. I believe gets you that number. Any questions on that? Yeah, I go through now. Just like before, we want to check which one doesn't make sense or really won't work. So just to remind ourselves here, I'm going to just rewrite our equilibrium line from our ice table so we could kind of help us make that decision without flipping back and forth. So we go back to our equilibrium line on our ice table here. For the H2, it was 0.00623 minus X. For the I2 is 0.00414 minus X. And for the HI, it was 0.0224 plus 2X. If you're not sure, right, the top number here is 0.014, right, or 0.0114, this number right here. 0.0114 is too big to put into here. That's going to give us a negative number. So this one is too big. That would mean that hopefully that should be our correct X value in this case. So if we pop that one in for each of them, now we could get our concentrations. So our H2 at equilibrium will be 0.00623 minus our X value of 1.56 times 10 to the minus 3 molar. And that is going to get us, come here, 0.00623 minus 1.56 to the minus 3. Looks like 4.67 times 10 to the minus 3 molar. For our I2, it will be 0.00414 minus our X, 1.56 times 10 to the minus 3 molar. 0.00414 minus 1.56 to the minus 3. That's going to get us 2.58 times 10 to the minus 3 molar. And lastly, our HI at equilibrium going to be 2, no, not 2, actually, there's initial number there, 0.0224 plus 2 times our X value, 1.56 times 10 to the minus 3. And that's going to get us 2.55, I'll call it. 2.55 times 10 to the minus 2 molar in that case. That's lots of some fun math, yeah. And again, if we check ourselves here, I don't really want to know if I screwed up, but let's check ourselves just to make sure. We put that back in, we'll take our HI and square it, divided by our two other ones, 4.67 to the minus 3, divided by 2.58 to the minus 3. That's like 54.1. That's pretty darn good, I think. Yeah, not too bad. Any questions on that? So you can see the quadratic we did earlier, not as complicated as this. They can get very complicated. You want to make sure you kind of keep everything clear along the way, that you do not maybe transpose a number, add an extra zero, stuff like that. So again, maybe something like significant scientific notation is good if you got a lot of zeros working there, so those don't mess up. Also, a really good idea, like I said before, throw it back in to make sure it is close, because definitely a lot of room for error in sort of this type of calculation. Any questions on that one? That should have woke up your math, hopefully. All right, so let's try one last one to finish it up here for today. The Kp value of 4.3 times 10 to the minus 4. Calculate the pressures in atmospheres for each of these guys. If we started with 0.862 atmospheres of N2, 0.373 atmospheres of H2. So give it a go, see what you come up with here. So since we are getting to the end here, let's go through this one. And you might be at the point where you're like, I don't want to do the math at this point, right? That's probably where you're at, most of you. I was at that point about 5 minutes ago. But let's take a look and talk about how we could kind of work through this one here. All right, so obviously we're going to do a ice table here. It's an equilibrium problem. As I mentioned earlier, it doesn't matter if it's Kp and pressures or Kc and molarity. It all works the same. You do it all the same. The only thing when you are dealing with pressures, as we talked about, you just want to make sure they are in atmospheres when they go into the ice table. So we're going to start with our expression, which would be obviously our Kp expression here, which is the partial pressure of NH3. And we still need to square it, even though we're dealing with pressures. It works the same way as concentrations. Partial pressure of N2, partial pressure of H2. And again, we want to make sure we cube that because of the coefficient there in the equation along the way. That's going to equal our Kp value of 4.31 times 10 to the minus 4. Unlike the previous problem here, we're not given pressures of our products. We're just given pressures of our reactants, which means we don't have to worry about Q in this situation because we can't calculate it anyways, right? So we can actually go into our ice table here. So we'll go N2 plus our H2, doing a little 2NH3. So initially here in terms of pressures, we got 0.862 atmospheres. We got 0.373. And again, just like in concentrations, we could assume 0 there on the product side since nothing was mentioned. That also tells us, just like it did earlier, this reaction definitely has got to go in the forward direction because we have no products. So we're going to go minus x here. This is going to be minus 3x. And that's going to be plus 2x on the other end there. Again, making sure we take our coefficients. That's going to drop us down here to 0.862 minus x, 0.373 minus 3x, and 2x. First off, any questions on the table there? All right, so we're going to go into our expression. That's going to give us a 2x squared up on top. That's going to give us a 0.862 minus x and a 0.373 minus 3x. That's going to be cubed, and that's going to equal our 4.31 times 10 to the minus 4 in this case. And really at this point, clearly the right answer is just to go to the next problem because nobody should do this one, right? All right, so clearly we don't want to actually do the math on this one here, right? Because we'll be here all week. So we want to look at it and see if maybe we can figure out maybe a way that we can maybe get around that math. So the first thing that we want to look at to help us maybe make this decision is my K value here, right? And when I look at my K value, is that K value considered a large value or a small value? That is a small value of K, right? Less than 1 is a small value of K. And when you have a small value of K, would you expect at equilibrium to have mainly reactants or products present? It is going to be reactants, right? Since products, right, divided by reactants. So the only way to get a small K value is you need a larger amount of reactants, right? And a smaller product. So when you divide that, you get a small number. So what that means is when we reach equilibrium, we should actually expect perhaps more reactants than products. And because we're going to expect more reactants than products, that means that the change that's going to occur here is not going to be all that much because it's basically going to hang out on the reactant side. A little bit of it will go the other way, but not a lot. So when you have a situation like this where you do have, and I'm just going to rewrite it right here, 2x squared, and what we got there, 862,373. Right? Oops, that was cubed. I think that one, if I'm not mistaken. So it was 3x, right? Yeah. And 4.31 to the minus 4. So since this K value is small, we could assume in this case that x is going to equal 0. And now we cannot assume that all x's are going to equal 0 because you would have, frankly, nothing to solve for at that point. So the x's that we're talking about that we could assume is going to equal 0 are any x's that you're going to subtract from a number are any x's you would be adding to a number. So these are the x's that we would assume will be 0 in this case. The reason we cannot, for example, assume that the top x there is going to be 0 is we are starting with how much of that guy? Starting with nothing, right? Which means if you make anything and you had nothing to start with, that's pretty significant, right? You started with nothing, you made at least a little something, right? So besides the fact you have nothing to solve for at that point, get rid of it. We don't zero that one out because it is significant. The changes we see here are going to be negligible or 0 is our assumption. So by doing that, that turns this into 2x squared divided by 0.862 times 0.373 cubed equals 4.31 times 10 to the minus 4. I would much rather solve this one than the previous thing that we just saw. Yes. It is because the K value is small in this case. And because of that, when we reach equilibrium, we would mainly have reactants, which means since this reaction is heading in the forward direction, we're going to end up with mainly reactants, which means not a heck of a lot's going to make it over to the product side. And the change that's going to happen for our reactants, because it's going to not really move that much, where they start with and where they end with is going to be negligible. It's going to be a very small amount of change that's going to occur because of the K value. The official cutoff is anything that is considered a small value of K, you could give it a go. Okay. And we'll talk about in just a second how you should maybe check yourself if you do something like this here. Yeah. Other questions? Okay, so now we could clean up this, right? We're going to multiply these guys together. That's going to give us 4x squared on top. That's going to give us here don't forget to cube the bottom guy there, 0.373 cubed. Times 0.862. That's going to get me a 4.47 times 10 to the minus 2. I think I'm still in scientific notation over here. And that's going to be 4.31 times 10 to the minus 4. We're going to multiply that to the other side. And then I'm going to come back after I do that and divide by 4. Okay, so I'm just going to do two things at once here. So I'm going to multiply the 4.47 times 10 to the minus 2 to the other side times 4.31 to the minus 4, and then I'm going to divide by 4, and that will essentially give me x squared is equal to 4.82 times 10 to the minus 6. At this point, I could do a little square root action on both sides, and that's going to give me an x value of 2 we'll call it 20 times 10 to the minus 3 in this particular case. First off, any questions on that? Now, the important thing here is if you make this assumption, you do have to check it to make sure it's okay. And the rule that we use to check it is what is known as the 5% rule. So basically, if it is 5% or less, you're good. If it's not 5% or more than 5% and higher, you're not good, and that means sadly back to quadratic you go. Yes, you got to kind of go solve it some other way. So to check it, you're going to take your x value and you're basically just going to divide it by the number you're going to add it to or subtract it from, whichever that is, and times it by 100%. So in this particular case, we would take our 2.20 times 10 to the minus 3. We would divide it, for example, by 0.862, as that was the number we're going to subtract it from. We're going to times it by 100%, and we're going to hope we are less than 5%, which I think in this case we're at 0.25%. So that is a good check. By the way, you can check both. If one works, typically they're both good. But if you were going to check the other one, since that really is 3x, you technically would take 3 times 2.20 times 10 to the minus 3, divide it by 0.373, and times it by 100% as well. And there it is, thinking. All right, 3 times 2.2 to the minus 3 divided by 0.373 times 100. That's a 1.8%, also less than 5%. So that's happy faces all day, right? So you don't have to go back and solve some other way. Again, if you got higher than 5%, you would need to go back, and for our purposes, you would have to probably do the quadratic formula to solve that sort of problem. Now that we know that's good, we have our X value. We could put it into our answer here. So our pressure of, I think it was H2, would be 0.862 minus 2.20 times 10 to the minus 3. So that's going to go 0.862 minus 2.2 to the minus 3. Going to give us 0.860. Remember, these are pressures, so these are actually atmospheres. Our pressure at equilibrium of H2 nitrogen, I think. Hopefully I didn't get that backwards. Was that nitrogen, the first one? No, it was nitrogen. Huh? So that's actually nitrogen. Bad. This is H2. And that would be, in this case, 0.373 minus 3 times our X value. And that's going to be 3.3 minus 3 times 2.2 to the minus 3. Going to get us 0.366 atmospheres. And lastly, our pressure of NH3 was just 2 times our X value, 2.2 times 10 to the minus 3. And 2 times 2.2 to the minus 3. Going to get us 0.0044 atmospheres in this case. And again, if we stick that back in there, hopefully it works out, I hope. Let's see here, 0.86. I thought 0.366 cubed. About 4.6 times 10 to the minus 4. I hope that was the exponent there, with a little bit of rounding there. So any questions on that? So once again, if you have a small value of K, you can make the assumption. You should always check the assumption to make sure it works. It will not work 100% of the time. Last question before we get out of here. Why did we not do the assumption on the previous ones? The K value was 7, which is considered large. The other two is 54.3, which is also considered large. So you cannot do it because the K values were too big. All right. Ice table extravaganza today. We'll wrap it up there.